time complexity of this function is O(n), because the for loop iterates through all elements of the array one by one. There is an if condition for each element, and for negative numbers, a multiplication and addition operation is performed. However, since these operations run in constant time, the overall complexity remains O(n). Um, in other words, as the input size increases, the execution time increases proportionally. And now in here, the first three loops running O n square, O n square, and O n, and because the number of iterations is proportional to n or n square, the loop with e plus 2 also runs in O n square, since it iterates around n square over 3 times. The loop with a fixed limit runs in O1, because the number of iterations does not depend on n. Loops that grow exponentially complete in O log n time. The decreasing loop also runs in O1 as it terminates in a fixed number of steps. For nested loops, the complexities are calculated by multiplying them, uh, O n m and O m log n. In summary, some loops have linear, others have logarithmic, and some have multiplicative time complexity. The overall complexity depends on how the loop increments are structured. This function performs exponentiation using the divide and conquer approach. Since n is divided by 2 at each step, the time complexity of the function is O log n. This means that even if n is a large number, the number of operations decreases logarithmically, making it much faster than the classic Ln exponentiation method. Um, the function calls itself twice in each invocation, a recursive fib n minus 1 and a recursive fib n minus 2. This results in a recurrence relation for the runtime Tn. This recurrence follows the same growth pattern as the Fibonacci sequence itself. Since Fibonacci numbers grow approximately by around 1.6. The time complexity of this function is O2n. This is exponential complexity, which is very inefficient because the computation time increases rapidly as n grows. Uh, a more efficient approach would be use dynamic programming or an iterative methods. Now, we have two computers. A fast computer, which is 10 times faster than slow computer. And we have two algorithms, a fast algorithm with O and time complexity, slow algorithm with O and square time complexity. Now let's compare. first slow algorithm on fast computer. The fast computer is 10x faster, so the execution time approximately n square over 10. And second, fast algorithm on a slow computer. The algorithm runs in O(n) time, and so the execution time is n. To determine which is faster, we compare n square over 10 versus n. For small values of n, the slow algorithm on the fast computer might seem competitive. However, as n grows, n square increases much faster than n, and making fast algorithm the better choice. So for a large n, the fast algorithm running on a slow computer is always better than running a slow algorithm on a fast computer. This proves that choosing a better algorithm is more important than just using a faster computer.